accelerating expansion. Some of those will go out of sight because space will be growing so fast, light can't get to us from them. So there'll be an issue there. But if things were reasonable, if you waited long enough, you would see galaxies form and see that structure confirmed. Here, we have to do it statistically. Just like I said, you see the 1-year-old trees and the 2-year-old trees, and you see the pattern, and you see your model of how a tree grows, and they match, right? And you can see how it goes. So we do have predictions, but we don't have the patience to wait the billions of years to see right now. Maybe later we will have.
Okay, sir. Thank you, sir.
Thank you.
Ladies and gentlemen, due to time constraint, we may only allow 3 more questions. I appreciate if one person can just forward 1 question. Thank you.
So we'll do this one over here, and then we'll go back to you.
Hi, Professor George. I would like to ask a bit about Big Bang Theory. And you have once said that your research team is keen on understanding the Big Bang in order to predict the future of the universe. And Stephen Hawking once claimed that if the rate of expansion 1 second after the Big Bang had been smaller or slightly higher, we won't have the universe that we have now today. So my question is that the Big Bang happened by chance, or the Big Bang follows some mathematical equation? And another question is that if the universe did apply some mathematical equations, if the Big Bang were to occur again in the future, will we get the same universe as what we have today? Yes, thanks.
All right. So this is a question. This is a mixture of philosophical and scientific questions. And so the interesting thing about the universe we're in now is a lot of what shows up is by chance, but the overall structure of the universe is actually fairly well determined. It's like when you ask 2 voters how they're going to vote, you can get a very wildly answering. But when you ask 1 million voters, you get a very good statistical thing. So we have 100 billion galaxies, so we have pretty good statistics on how galaxies form and so forth. We haven't studied them all, but we're beginning to study them. And so the question is, how repeatable is that? And the answer is, there are some things that automatically adjust in the universe so that the expansion rate and things will take care of themselves. It's the very beginning, when you're first forming the structure of space-time, that it matters. And then once you have that, the universe will adjust itself, and the formation of galaxies may happen a little earlier or a little later. But what becomes critical is that you make it through that early period, so you can create enough space-time that you have a big enough universe to have a good sample. But we can only see a limited part of the universe. We have reason to expect that the universe is much, much bigger than the 14 billion light years we can see in every direction. It could be very many orders of magnitude greater than that. So when I say there's at least 100 billion galaxies, that's that ones we could see. There could be many orders of magnitude greater than that. There could be 10 to the 5th or 10 to the 10th times more galaxies out there. And then you'd have a good statistical sample if you waited long enough to sample that. So I invented this term, which we call cosmic variance, which really is short for cosmic sample variance. We're limited to see only a certain volume of the universe because that's all the further light can travel in the story of the universe. But it's still a pretty big sample, and the fluctuations aren't that large, except in the things there are only very few of. So when people are zooming in on that one particular huge cluster of galaxies, you don't have billions of galaxies. You may only have 1,000 of structures like that, and therefore you begin to have less of a sample and less certainty in it. But now one of the questions is, if you go back to the very beginning of the universe, if you have fluctuations in the parameters, does that actually change some of the fundamental parameters of physics, or does it just make the random variation a little different? And if I look on a big enough scale, I'll get the same average answer. And that's something we don't know the answer to. We speculate on it, but we don't have enough observations and enough constraints on our theories to tell us, if you made the universe over and over again, which is one possibility in some models, you make many samples of the universe, what we call the universe, but there are many, it's only a portion of a much bigger universe where there are many different samples. If the laws of physics might vary, and some of them are very hospitable to life and some are not so hospitable to life, because some are going to make a lot of stars which are stable and last a long time, and some won't make stars, right? And so we don't know what the case is. We're not surprised we find ourselves in a universe that has a place that's stable and conducive to life, if that was a variation. but it's a very tricky thing to do because you're doing posterior probability on something that's an infinite sample. One of the things that can easily be is the universe is infinite, and there are infinite many tries at making universes, and therefore doing your statistics properly is a really tricky business because you only know the answer, you don't know the premises to begin with. So it's an interesting problem, but we're not quite equipped to solve that kind of a question yet. So, yes?
My name is Wan Ahmad Faisal, a final year student in chemical engineering. I've gone through your book, Wrinkles in Time, last week in the bookstore, and also watched your videos in the TED Talks. And since I have prepared a few questions, since the MC doesn't allow me to go further, but I will ask you one final question. In modern or this so-called postmodern era, one of the great crises is the poverty of metaphysics. Would you agree that for modern science to remain relevant, especially your own field, astrophysics, we need to integrate the element of metaphysical science into the scientific research? That's my questions.
All right. Well, we could debate and argue about this. I don't think that science has a poverty in the sense that there's tremendous richness of possibilities in science and a tremendous number of new things to be discovered and understood. But science is not all there is to the world. You still have to decide what you're going to do with your knowledge and your innovations, what products you're going to actually make and that people will buy and use. And we have a kind of a market system that makes those kinds of decisions. But you also want people to understand science and have a perspective so that they can then use other judgments, moral and ethical judgments, to decide what are really good things to do. And so I wouldn't say that science itself is in poverty. I would say science is not a complete decider of what everything should be. But right now, we need science in order to keep our economies going strongly. We need science to solve certain global problems like climate and energy that are coming up. And we need science to improve the medical care and health of people to make it so we can make it so that people can have long life expectancy and good health so that they can do their good work and also enjoy their lives very much. So it's not that science is everything, but that science has tremendous benefits to bring to society, and we have to be able to pursue the science and find out what we can to really take advantage of it.
Good afternoon, sir. My name
Good
is
afternoon.
Dhanaraj, second year, first time chemical engineering. I just wanted to know, want to know, what is beyond the universe? I'm very curious on that. What do you think is beyond the universe?
Okay, so there's a simple answer and then a little more complicated answer to the question. So imagine the very simple situation. The Earth you think is roughly a sphere. Now imagine it's idealized as a perfect sphere. Every point on the Earth, on the surface of the Earth, is equivalent. So I'm suppressing one dimension and only letting you live in two dimensions. Is there any special point in that sphere? The answer is no, because I said every point was equivalent. So now we have a north and south pole because the Earth is rotating and we have a coordinate grid. But you could, if the Earth was not rotating, you could swivel the Earth around and it's completely rotationally invariant. Every point would be equivalent. And there's also no edge, no beyond, it's bounded, it's finite and bounded. You can also imagine a universe that's infinite. So think of a plain sheet that goes to infinity in all directions. And infinity means not to an edge, but forever. No, you keep going and you keep going and you keep going. So there's a simple geometrical topological answer. You can either have a closed space that has no boundary, right? So there's no boundary condition. You can make spaces like a sphere or like a cylinder or something where there's no edges. This goes to infinity in one direction, it's finite in the other direction. Or an infinite plane, right? You can make very easily and understand in two-dimensional objects in three-dimensional space because our brains are designed for three-dimensional space. You can understand such objects that have no boundaries and either go forever or are finite. And so then the question is, well, what's before the beginning of time or what's outside the universe? There isn't anything on those kind of situations. But there's another possible solution, which is there is a beginning of time, but outside the universe is even a more spectacular universe that's accelerating its expansion all the time. And so almost the entire full universe is taken up in an accelerating part, but every now and then a little tiny piece has a quantum fluctuation that breaks it off. and then it goes into the decelerating mode, and we get something simple like the universe we see, which is very much larger than what we can see, but makes the galaxies and so forth. And that's just like, you know, sesame seeds on a giant roll that goes forever, right? So that most of the universe is the sesame seeds, is the roll, and only a tiny fraction are sesame seeds, and yet that sesame seeds holds hundreds of billions or more galaxies easily, right? So the scale that you can have is so forth. So your answer about what's outside has to do with what the universe is really like, and also what your definition of the geometry and topology of the universe is. And there can be very simple universes that just exist and are finite, and there can be very complicated universes that are not only go forever in all directions, but have very complicated topologies. And we don't know for sure, but we know the universe we're in came in such a way, it created a very simple topology for the part that we can see. We know that it's very big and it's growing, right? That we can understand. So we have one last question. Oh, we have two last questions, huh?
Good afternoon. My name is Muhammad Biasa Azari, Foundation, first semester. I would like to ask about annihilation process or total destruction involving antimatter. And please give some phenomena involving this process. And could you explain the prospect to use in annihilation process for the source of energy of the future?
All right. So for those of you who don't know, one of the things that's very necessary in the universe and is shown to exist in the universe, it's necessary for cause and effect to be valid. And being scientists and engineers, we like for there to be a rational so forth. We think cause and effect is very important. But the fact is, it's verified. For every particle there's an antiparticle, which has exactly the properties of that particle, but with the properties so that when you add them together, you get pure energy. And that allows, when that happens, that allows for cause and effect to be valid no matter what frame you're in. And so we understand for lots of reasons that in the very early universe, we had a kind of a chemical equilibrium, but it's a chemical equilibrium in the hydrogen physics, not in chemistry. But you have chemical equilibrium in nuclear physics and high energy physics in the weak interaction, everything else. And when you get to sufficiently high energies, you will produce equal, the energy gets spread equally in every possible state. And some of the possible states are antimatter and matter pairs, right? So we know that in the very early universe, there is essentially equal amounts of matter and antimatter. And one of the problems we have is that means there should be equal amounts of matter and antimatter in the present universe unless some process came and gave us a slight excess in the early universe so that we could be made of matter. So one of the early sets of experiments that I did as a new PhD was to search for this antimatter. And we were in our experiments able to show that in the particles that come to us from around the galaxy, that less than 1 in 10,000 of those could be made of antimatter. We didn't see any positive evidence for antimatter, but we searched through 30 to 40,000 particles and tested to whether it was antimatter or not, and none were, as far as we could tell, antimatter. And at that point, I said, okay, that means there's no antimatter stars or anything. I should go into working on something else. But what that means is antimatter certainly exists, but it doesn't necessarily exist on large scale, so that it's in planets or stars or so forth. So the other way you can tell, you can look at clusters of galaxies, and if one galaxy is made of antimatter and the other one's not, which is what you would infer from the fact there's none in our galaxy on a significant scale, then you would say when an anti-galaxy came near a matter galaxy, that the gases, when they collide, would annihilate, and you would see this huge eruption of energy and gamma rays coming to us. And you don't see evidence of that. So you can kind of guess the matter is separating even more than that. So if you want to solve the energy problem by finding a big mine of antimatter, that seems unlikely. If you want to make a really good battery by making a bunch of antimatter and storing it in a magnetic container and letting a little leak out to annihilate with matter, it's a very effective battery because you get 100% conversion of matter to energy when you do the annihilation. So that's why in the Star Trek they have the matter-antimatter pods. It's the most efficient way for the writers to give